My name is Tasni Fatima. My project topic is medical diagnosis using Bayes theorem for gestational diabetes prediction. The main objective is to predict the gestational diabetes mellitus using Bayes theorem, and the specific objectives are apply Bayes inference to calculate the posterior probabilities of GDM and develop a probabilistic framework for early diagnosis and enhance decision making in maternal healthcare. GDM means the gestational diabetes mellitus affect 9.2 pregnancies globally with a significant health risk. If a mother have a GDM, then it will adversely affect the health of the child, and after the delivery also the child need to affect will the child also get the effect of the mother's gestational diabetes. For the solution is the Bayesian modeling update probabilities of GDM based on risk factors and test result. This will help in the Bayesian modeling will help in the prior or the early detection of the gestational diabetes. Outcome: a probabilistic approach using Bayes theorem improve predictive accuracy and clinical decision making. What is a GDM? GDM is a gestational diabetes mellitus, which is a pregnancy-related condition with the parent having a high blood sugar level. It can be diagnosed between 24 to 28 weeks of pregnancy. Why Bayes theorem used in medicine? This provides a mathematical framework for updating probabilities based on evidence, facilitates informed decision making and risk estimation. What is Bayes theorem? Bayes theorem is P of H given D equal to P of D given H into P of H by P of D, where P of H given D is the posterior probability of it is the posterior probability of the given data from the GDM. Then P of D given H is the likelihood data, and P of H, probability of H, is the prior probability, that is the initial risk of the GDM, and then P of D is the marginal probability, which is the normalizing constant. Okay. Then interpretation: update the probability of GDM as a new data become available. Then methodology: here in my data set, the features are age, pregnancy number, BMI, hereditary prediction. In data pre-processing, we need to handle the missing values. There may be missing values, so we need to handle that, and there will be the values may be vary in different ranges, so we need to normalize or standardize that values using the standard scalar. And in the Bayesian step, we need to first calculate the prior probabilities, then we need to derive the likelihood functions, then we need to normalize using the evidence, that is P of E. Then compute the posterior probability. We need to finally compute the posterior probabilities. The mathematical formulation: prior probability is the proportion of GDM cases in training data. Is this the proportion where how many GDM cases are there? Then likelihood function, which is the probability of features given GDM, which is the whole product of probability of features given GDM. Then posterior probabilities: P of GDM given features is equal to P of features given GDM into P of GDM by the whole by probability of features. The program overview: we are using the libraries like pandas, numpy. Then the Bayesian formula function we are using here. We are using the Bayesian theorem as a function. So if we need the equation, if we need that Bayesian theorem in any other part of the program, we can just call that out. Okay, we in the Bayesian theorem we are returning likelihood into prior by or the whole by evidence. Then we need to test the we need to train, and also we need to test to ensure the effectiveness of the program, and we need the standard scalar for standardization. And key equations in the code are: likelihood. For finding the likelihood of GDM, we can take x train of y train equal to 1, that is when the output is positive, or the person with the GDM it will give 1, and for person without GDM it will give 0. So for the positive case, y train is equal to 1 with the mean of, and we need to evaluate the mean of in the axis row, in the feature row we need to evaluate the mean. And in the same way we need to find the likelihood of non-GDM using this y train equal to 0 and mean in the axis, same mean in the axis of 0. For posterior calculation, we need the Bayes theorem. The Bayes theorem, which already called as a function, that Bayes theorem of prior GDM and likelihood GDM we are calculating just earlier, and then evidence sample, which is the evidence which which is a constant. Then we also need to calculate the posterior not GDM, Bayes theorem, prior no GDM, likelihood no GDM sample, evidence sample. Okay. And then by doing all this, I get a accuracy of 75% with a confusion matrix of true positive of 153, false positive of 0, and true negative of 0, and false positive of 50. By analyzing the result, the observation is high precision but lower recall for predicting non-GDM cases. That is a drawback. And then potential improvement, we can use data augmentation or oversampling, and feature engineering to include more medical factors, and we can use hyperparameter tuning. Conclusion. Bayesian modeling proves effective in predicting GDM with a moderate accuracy. It has not that much high accuracy. After doing all the hyperparameter tuning or the correct feature selection, we can improve the accuracy. But here we only have a 75%, which is not that much good accuracy. So it is effective in predicting GDM with a moderate accuracy. Then accurate updating of probabilities aid healthcare providers is in early diagnosis. After improvement, we can use this in healthcare. Then room for refinement or through advanced modeling techniques and a larger data set. Future scope, we can incorporate additional features like a blood pressure or glucose tolerant test result, etc. Then explore ensemble method like a random forest with the Bayesian adjustment, or we can validate the model on diverse population to improve the generalizability. And these are the references, and thank you.